Bismillahirrahmanirrahim. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. Okay, welcome to the Forensic Analytical Instrumentation. Today we will learn on the first chapter, on the first part of the spectroscopy. Okay, my name is again Dr. Muhammad Afiq bin Muhammad Nuri. Alright. Next we will go to the course outline. Okay, here is the course outlines of the study. Okay, first thing first, I will describe about the importance why we need analytical instrumentation. It's not just based on the spectroscopy, but it's until all the instrument that we will learn in this course, including the chromatography and also the, for example, what we call microscopy. Okay, and then only that we will go directly into the spectroscopy topic. On the introduction, we will learn the differences on the terms spectroscopy, spectrometry, and also spectrum. And then we will go back to the basic on the types of electromagnetic radiation interaction available. And then we will go into the classification of spectroscopy. Okay. And then we will somehow try to understand the differences between molecular spectroscopy and also atomic spectroscopy. Next, in this study, we will learn about the Beer and Lamberts Law application during spectroscopy technique, in the spectroscopy technique. We will also learn about the types of spectroscopy available. Then we will look into the components of a spectrometer, the basic components of a spectrometer. And then we will look a little bit about the spectrometer design. And then after only we understand all of this, we will continue to learn a few kinds of the spectroscopy techniques that listed in the types of spectroscopy. We will not learn everything, but we will learn the few important ones. Or I say that readily available in the faculty, so it much easier for you guys if you need to use the instrument later on. So we will learn about the common spectroscopy in the next part. But for this part, the part 1 of the spectroscopy, we will only learn until the spectrometer design. Okay, first thing first, let us know why we need analytical instrumentation. Okay, if you look on the figure here, they ask, today everyone has to know what's in the food, what's in the water, what's in the air. This is truly the golden age of the analytical chemistry. So today's everybody worried about what they have in their food. If there is poison inside there, or for example, if they're smoking, is there any toxic compound inside there? If I'm as the police, I want to know, is the water he drinks or she drinks contain drugs or not? Okay, so when there is a question, we need to supply an answer. To supply an answer, we need to solve the problem. Okay, to solve the problem, that is the why we need the analytical instrumentation. Okay guys, again, if you have any problem or if you cannot understand why whatever I'm teaching you, especially on that particular slide, you can somehow just do a snapshot and send to the WhatsApp group so I can answer your question. Okay, the next one, for example, here in the newspapers here, we can see that the river contaminated with something color blue in color. So you have river water sample contaminated with blue dyes, maybe something else, we don't really know. So the question, why is the thing made the water blue? What is the compound? What is our analyte of interest? And the next thing we know, can it harm us, or how much it is inside the river? Okay, because when we say can it harm us, we need to know the toxicity. Okay, and then we need to know the amount of the target compound. Okay. Okay, for example, paracetamol, if we only take one tablet, it should be okay. But if we take dozens of paracetamol at one time, we can be dead. Okay, let's look into the next one. Okay, here in the picture, I think everybody already know about Dr. Noor Law. 7 products of cosmetics was detected containing a toxic compound, okay, containing poison. So this is the thing that why we need analytical instrumentation. We want to know what kind of the poison inside of the cosmetic, what is the amount. Okay, and here is the another online newspapers that told us that forensic evidence is the silent witness that can help the investigation. So, to analyze the forensic evidence, forensic analytical instrumentation is among the main character that can help to assist the investigation. Okay, let's look into the introduction, and we will begin the introduction by understanding the definition of the specific terms. First thing first is the spectroscopy. The spectroscopy is the study of the properties of matter through its interaction with different frequency components of the electromagnetic radiation spectrum. For example, here is your matter or your analyte of interest or the target compound. So we make our matter or the target compound interact with different frequency of components of electromagnetic radiation. Okay, for example, at the IR, they have their range of frequency that we interact with our analyte of interest. For example, if we do the UV analysis, we apply different kind of the UV wavelength to our analyte of interest, to the matter of interest. Okay, so let's look. For example, here is the light source. Okay, it goes to the analyte of interest. Analyte of interest, they have the initial state, and then after interacted with the what we call the line over here, it will absorb one of the frequency. For example, we have one frequency, it absorb one. So if we look over here, the spectrum, so it gives one missing color because one of the frequency absorbed by the analyte of interest. Okay. I cannot pause these figures because this is a GIF figures. It's a continuous figures. If we look over here, we have the let's wait for a while. We have the absorption and the emission spectrum, right? So the absorption, when we give the spectrum here, okay, for example, the orange one is absorbed by our analyte, so here is the absorption spectrum. So when our analyte goes down, it will release the energy, so it will give the emission spectrum. Okay, let's look into this illustration to make you guys learn back to the basic again. Here is our analyte of interest. It has 2 orbital, lower orbital and the high orbital or inner orbital to the outer orbital. Okay, so here is the frequency or electromagnetic radiation that we want to apply to our analyte. And here we have the blue, red, and orange frequency of electromagnetic radiation. Let's just put the radiation we use is the UV. Let's say we have the blue UV, red UV, and the orange UV. Okay, then after it's interact with the analyte of interest, okay, not all the frequency will be absorbed by of analyte of interest. Only a certain frequency will be absorbed. For example here, let's say in this matter, our analyte only absorb the red one. So after absorbing the red frequency of UV, the electron here will move to the outer orbital. Okay, so the other two frequency is not absorbed, so when it reach the data reader, it will show the absorption spectrum. Okay, so at the absorption spectrum, because of the red one is absorbed by the analyte of interest, only blue and orange were displayed. Only blue and orange will be displayed. Okay, after some while, our analyte, the shell at the outer orbital will relax back to the lower orbital. Okay, so when it goes back to the lower orbital over here, it will release the frequency that the analyte absorbed just before this. Before this is absorbed red, right? So after a while, the electron will go back to the inner orbital and it will release the spectrum that the analyte absorbed. In this case is the red one. So when it release the red one, the data reader can read the emission of the red frequency. So it will display the red frequency of absorption. Okay, this is the idea how the interaction between electromagnetic radiation at different kind of frequency and also the analyte of interest. Okay, the next one we will learn about the types of electromagnetic radiation or spectrum. Okay, here if we can see from above one, we have a lot kind of the electromagnetic radiation, but the only range that are visible to human eyes is this within this range. Okay, other than that, we cannot see by our naked eyes. Okay, if we can see over here, that is the size of the spectrum. Okay, as the wavelength becomes shorter, the size of the radiation become more smaller. But when it becomes more smaller, the energy of the radiation become more higher, so it will become more dangerous. Compared to the radio frequency, it is very large, but it's not as harmful compared to the gamma ray. Okay, that's why we can hear radio using the FM frequency, for example, because the wavelength is so huge, so it can pass the human and buildings. Okay, but for the gamma ray, it will not go that far, but it is very dangerous. Okay, if you look over here, if you compare the temperature between all the kind of radiation, the temperature of the gamma ray is very, very high. Let's say for example, on the microwave side is about 1 Kelvin only, but on the X-ray and the anti-X-ray to the gamma ray in more than 10 million Kelvin. So you can imagine the differences between the shorter wavelength and the higher wavelength, between the gamma ray and also the radio wavelength. Okay, To present the models of the electromagnetic radiation, we can have two kind of the model. The first one is the wave model, like a previous slide, the wave model, represented by sinusoidal wave traveling in space with an oscillating electric field and perpendicular magnetic field. Okay, the wavelength is the complete cycle of the wave. For example, you have the starting point at the up until it goes up again. This is the length of wavelength. Okay, as the wavelength become longer, the energy become shorter. The energy become lower. But when the wavelength become lower, the energy become higher. Okay, this is the first kind of model of electromagnetic radiation. Okay, in the second model, we view as the particle model. Is light viewed as discrete particles of energy called photons. Okay, here is the photons, the discrete particles of energy. Okay, here we have the electron at the lower orbital and electron and also the higher orbital. Okay, let's say energy hit the particle and then the electron at the lower orbital will be sighted into the outer orbital, or we can say the upper orbital or higher orbital. Okay, so it's not can be impossible to be asked in the test or in your final examination. Please draw two models of electromagnetic radiation. That's kind of the question that can be asked to you guys. Okay, the next one we will learn about the spectrophotometry and spectrophotometer. Spectroscopy is a principle. Spectrophotometry and the spectrophotometer is about measurement. When we have the metry words, the key words of metry of meter is about measurement. Okay, if let's say for example in the spectrophotometry, it tells us about the principle of measurement, how much of the electromagnetic radiation absorbed by chemical substance. Okay, in the spectrophotometer, it tells us about the analytical instrument used to measure the amount of electromagnetic radiation interact with an light of interest. Okay, again, don't get confused. Spectroscopy is just tell us about the basic principle of interaction between electromagnetic radiation and also an light of interest. And the spectrophotometry is a principle of a method to measure how much of the electromagnetic radiation react with the light of interest. And the spectrophotometer is the analytical instrumentation used to measure the interaction of electromagnetic radiation and also the light of interest. So if you guys be able to understand the concept, you guys don't need to remember every words over here. Okay, spectroscopy is a principle. Spectrophotometry is the principle of the instrumentation, and the spectrophotometer is the instrument. Okay, the example of the spectrophotometer instrument is the UV spectrometer, FTIR, AAS, and also, for example, HPLC UV is also one kind of the spectrophotometer instrument. Okay, so I repeat again, spectroscopy is the principle where we want to study the interaction between a light of interest and also electromagnetic radiation. How to use that? We use spectrophotometer. What is spectrophotometer? Spectrophotometer is the instrument to measure the interaction. Okay, the principle behind of the spectrophotometer is the spectrophotometry. Okay, remember, that is how you guys need to understand what the differences between spectroscopy, spectrophotometry, and also spectrophotometer. Again, spectrophotometer is the analytical instrumentation that we apply the spectrophotometry principle. Okay, spectrophotometry is to measure. Spectroscopy is to study the interaction. Okay, so we can say that the biggest chunk of the thing is the spectroscopy. Inside of this spectroscopy is the spectrophotometry. To utilize the spectrophotometry, we need the instrument. The instrument that we call as the spectrophotometer. Okay, I hope you guys don't get confused. Okay, the next one, we will learn about the definition of spectrum. Spectrum is the data obtained from a spectrophotometer. Okay, what is spectrophotometer? Spectrophotometer is the instrument. Okay, the spectrum is a plot of intensity of energy versus the wavelength or mass or momentum or frequency of the energy. Or we can say that a spectrum is the plot of intensity of energy versus the wavelength of frequency of electromagnetic radiation frequency. Okay, for example here is one of the one compound that measure using UV. Okay, UV we have range from 200 to about 800. Okay. In the previous example, we shows that that particular compound can only absorb the red and the light. Okay, so that only have 3 kind of different frequency, but now we have about 600. Okay, as I mentioned before, it's not necessarily that the analyte will be able to absorb 100% of the radiation. Okay, for example here, from 200 to 600, for example at 400 wavelength, okay, it can absorb about, let's say for example here, about 85% of the frequency at 400 wavelength. At 500 over here, it can only absorb only about 25% of the frequency. So this is the kind of spectrum we should be expected to get during the analysis. Okay, here is the infrared spectroscopy with a range of the wavelength. Okay, with the absorption over here. The principle behind it is about the same. So again, what is the difference between spectroscopy, spectrophotometry, and spectrum? Spectroscopy is a principle of all spectroscopy. Spectrophotometry is under spectroscopy, that is the principle to measure the amount of electromagnetic radiation. Under the spectrophotometry is the spectrophotometer, is the instrumentation tool that will be used to measure the absorption. And then the spectrophotometer will produce a spectrum, a reading, that is the plot of intensity of absorption or emission versus the wavelength of interaction. Okay, so there is a summary of the spectroscopy, spectrophotometry, and also spectrum. Okay, the next one we will learn about the types of electromagnetic radiation interaction. Okay, the first one we will look into the absorption. Absorption is the transition, or in other names is we can call also as the excitation from a lower energy state to a higher state. Okay, so we can divide this sentence into two actually. A transition from a lower energy state to a higher state with transfer of energy from radiation field to an absorber. Okay, we can imagine here is the radiation field. Okay, here is the absorber. Okay, so for the absorption, it must be done that the transfer of energy come from the radiation field to the absorber. Okay, so this is the second phase of the sentence. Okay, but the most important thing is in the first part of the sentence, a transition from a lower energy state to a higher state. That is absorption. It means when the source of radiation come into contact with the absorber or the light of interest. Okay, so we have the lower state here, and here is the higher state. Okay, so let's say your electron over here. So when the electromagnetic radiation come from the we can say radiation field come into contact with the absorber, the electron will excite or be absorbed, or we transit from the lower state. Here is the lower state, here is the higher state. So it will transit or excite. Better use the words excite to the higher state. Okay, this is what we call as absorption, a transition from a lower energy state to a higher state. With the transfer of energy from radiation come from the radiation field to the absorber or analyte of interest. Okay, how I can erase this thing. Okay, let me erase for a while. Okay, the next one is emission. Emission is to give off, or we can call as the relaxation. A transition, a relaxation from a higher energy state to a lower level with transfer of energy from the emitter to the radiation field. Okay, here is our absorber, here is the radiation field. In the emission, the transfer of energy come from the emitter, or previously the absorber, the analyte of interest. Now before this is absorber because it absorbed the radiation. Now the absorber become the emitter, with the analyte of interest emit the radiation to the radiation field. Okay, emit the energy to the radiation field. Okay, so what happen is like this. Okay, after the absorption, okay, now after a while, the analyte from the higher energy state, it will relax to the lower state. When it happen, it release the energy to the radiation field. Okay, so the next one is scattering. Scattering is the redirection of light due to its interaction with matter. So the analyte is not absorb or emit the light, but it's scatter the light. Might or might not occur with transfer of energy. Might or might not have different wavelength from incident light. Okay, so the not absorb, it's not absorbing, it's not emitting, but it's scattering. Okay, might occur or might not occur. Not every interaction will produce scattering. Might or might not have different wavelength from incident light. Sometimes whatever you hit scattered, it will produce the same wavelength. Sometimes you come out with this kind of wavelength, and then it will out with different wavelength. For example, it hit at 200 wavelength but exit at 250 wavelength. It can be possible. Okay, but scattering is not that much compared to absorption and emission. Okay, let's look closer into the absorption and emission. Okay, here is the radiation come from the radiation field, or we can call as the energy come from the radiation field. When it comes into contact with the absorber or analyte of interest that can absorb that kind of radiation, the electron from the analyte, from the absorber, will somehow excited into the higher state. Okay. For example, here it's absorbed and goes into the next orbital. In this situation, the radiation excite the electron next to the next two orbital. Okay. So this is the absorption. It goes from the lower state or ground state to the higher state, or we can call it as the excited state. For the emission, it's the vice versa, with the relaxation of electron to the ground state. The excitation of the relaxation of the electron from the excited state to the ground state, and then the energy from the absorber or from the emitter or from the analyte of interest emitted from the absorber from the emitter to the radiation field. Okay. So how about scattering? Okay. Alright. Scattering, most of the light will somehow, whatever heat will scatter also. So the amount of energy heat will produce the amount of energy scattered. That is the most of the scattered light. It means that whatever amount of light is not absorbed or emit, it will be scattered. Okay, most. Okay, but there is some situation where the scattered light interact with the molecule or analyte of interest, which is we call as the Raman scatter light. Okay, again I repeat again. When the radiation come into contact with the molecule and then it scatter, most of the light will be scattered. When the energy of the incident to the absorber released to the radiation field is the same, so we call as the Rayleigh scatter light. Okay, this is the majority of the scatter, the one that not absorb or emit, but only a minute 0.0001% interact during the scattering process. It means that the first we call as the Stokes-Raman scattered, and then the second one we call as the anti-Stokes-Raman scattered. Okay, the Stokes-Raman scattered is when it go to the virtual level of the excitation, and then it will go to the lower part of excitation, but the energy emitted, the energy scattered is less than energy of incident, we call as the Stokes. For the anti-Stokes, it happen when during the scattered, the energy after scattering is higher compared to the energy of incident, we call is anti-Stokes. So for scattering, you guys need to remember three things. We have Raman, anti-Stokes, Raman Stokes, and Rayleigh scattering. Rayleigh scattering, energy of incident equal to energy scattered back from the emitter to the radiation field. For the anti-Stokes, the energy produced is higher compared to energy of incident. For the Stokes, the energy is less than energy of scattered is less than energy of incident. Okay, I hope you guys not get confused. Okay, what is difference between the scattered and also the absorption or emission? As I mentioned before this, for the scattering, the excitation is only up to the virtual level. For the absorption and emission, is a different thing. You have a very solid ground of you have a very solid ground of excitation state. So here is the virtual level. You have another level like this. You have another level. Here is another level. Here is another level. For absorption, it goes to this excitation state. For emission, it goes like this, from the excitation state to the lower state. But for the scattering, the light only what we call goes up to the virtual level only. It's not to the excited state. It's not absorbed at all, or it's not emitted at all. Okay, so I hope you guys don't get confused, but don't worry, I believe the question will not be asked so much in your examination. Okay, this is another illustration of how about scattering. When energy of when energy of scattering is the same with the amount of energy of incident, so we call as the Rayleigh. When energy of scattering is less than energy of the incident, we call as the Raman-Stokes scattering. When the energy of scattering is higher compared to the energy of incident, we call as the anti-Stokes. So it goes up to virtual states. Okay, so how about fluorescence? Okay, fluorescence is other story. Fluorescence is when you go to the excited state. At the excited state, there are relaxation at the excited state. Okay, when the relaxation occur at the excited state, it will change the wavelength of the incident. So, for example, you hit with the green color, but it will go relaxation state. It will change the color to purple before it goes down. Okay, so for the absorption, okay, let's say I elongate this thing. Okay. So it goes from the, let's say for absorption, this case goes for absorption and then goes for the emission. Okay, for the absorption and emission, okay, it goes from the same excited state. It will goes to the back to the normal ground. But for the fluorescence, it will relax at the excited state. Let's say, if you can imagine like this, here is your compound. You have 4 orbital. Let's say for the normal process of the absorption and emission, let's say you come from the first electron here. So can I change the color? Okay, let's say, yeah, okay, why I cannot draw? Okay, then it will go to the higher level. Okay, so this is absorption. If goes back to original place, we call as the emission. So how about fluorescence? Fluorescence is when you give the electron excited to the higher state, but it relax to another energy level, high energy level, before it goes back to its original orbital. This is what we call as the fluorescence. Again, come from the ground level to the higher level, but at the higher level, it's relaxed to another high level before it goes back to the ground level. This is what we call the absorption. Okay, for the infrared we can imagine as the ground state. Okay, we can imagine as the ground state. It will not move to the excited state. It just play around the orbital. So it just like goes back up to here and then up until here only. It will not move to the another orbital. Okay, so the infrared is on the interaction within the ground state or vibrational state only. Okay, what we call as the vibrational. Alright. Okay, the next one we will look into classification of methods. Okay, the type of spectroscopy depends on the physical quantity measured. Normally, the quantity that is measured is an intensity, either of energy absorbed or produced. Most spectroscopic methods are differentiated as either atomic or molecular based on whether or not they apply to atoms or molecular. We will learn about this later on. Along with this distinction, they can be classified on the nature of interaction. Okay, we learn spectroscopy can be differentiated into the absorption, emission and scattering. In the method of analysis, we can also divide it into three: absorption spectroscopy, emission spectroscopy, scattering spectroscopy. I know, it's a little bit confusing. For me, supposedly, we call as the absorption spectrometry, emission spectrometry, or scattering spectrometry. That is the correct name if we allocate the classification of methods. But in the world of analysis, the general for the techniques of the method or the method we call as the spectroscopy as well. Absorption spectroscopy, emission spectroscopy, scattering spectroscopy. But also if you googling, you will also find absorption spectrometry, emission spectrometry, scattering spectrometry. It's all about the same. So for the absorption spectroscopy, it uses the range of electromagnetic spectra in the substance absorbed. This includes the atomic absorption spectroscopy and various molecular techniques such as infrared spectroscopy and nuclear magnetic resonance spectroscopy. As I mentioned here, we can divide it more our spectroscopy technique into atomic to molecular base. Okay, AAS here, AAS is atomized, molecular including IR and also NMR. IR, don't get confused with the abbreviation. Here is the here is the AAS, here is the IR spectroscopy, here is NMR. Okay, just abbreviation, don't get confused. In emission spectroscopy, it uses the range of electromagnetic spectra in which substance radiates. Before this, in the absorption, in which substance absorbed. Okay, and in the emission, in which a substance emit. The first substance must absorb energy before it can emit. Okay, the energy can be from a variety of sources, which determines the name of subsequent emission, like luminescence and other things. Okay, for example of the emission spectroscopy technique is the molecular luminescence technique, include the spectrophotometry, or you guys I think it's most common fluorescence UV, for example. Okay, I think that is another common thing you can heard. For the scattering spectroscopy, it measures the amount of light that a substance scatter at a certain wavelength. Okay, incident angles and polarization angle, the scattering process is much faster than absorption or emission process. Okay, emission spectroscopy is the longest one because we need the thing to absorb first. We need to wait before we can measure the emission. The absorption spectroscopy, we just measure the amount of radiation absorbed, but for scattering is very easy. It's more not easy, just very fast compared to the others. But I believe the very fast is about millisecond. It's not even a breath. Alright, one inhaling of breath. The difference is not that much. One example of the scattering spectroscopy or scattering spectrometry is the Raman spectroscopy technique. Okay, Raman spectroscopy is the principal, the instrumental is the Raman spectrometry. Okay, Raman spectrometer. Okay, right. Okay, you can imagine like this. The absorption spectroscopy is the classification. Okay, the spectrometer for the absorption spectroscopy is the AAS. the NMR and also IR. For the emission spectroscopy, the spectrophotometer for the emission spectroscopy is the spectrophlorimetry or the fluorescence UV. For the scattering spectroscopy, the spectrometer for the scattering spectroscopy is Raman spectrometer. Alright. Alright. Next, we will learn about the differences between molecular spectroscopy and also atomic. Based on name, I think you guys can differentiate already. Molecular spectroscopy is for molecule, meanwhile for atomic spectroscopy is for atom. Okay, we can imagine like this. For example, the compound is an ACl. Sorry, I need to open the pen. First of all, it's NaCl. Okay, if you want to analyze the whole thing as the NaCl, we need to go for the molecular spectroscopy. But for atomic spectroscopy, for the atomic spectroscopy, we need to analyze the single component only, which is, for example, Na plus or Cl minus. Same goes to the other thing. For example, we want to analyze potassium, or we want to analyze arsenic. But usually for the atomic spectroscopy, focus for inorganic element. For organic element, of course, we have only we have carbon and hydrogen and also oxygen. So it's not suitable for atomic spectroscopy. Atomic spectroscopy more suitable for inorganic element. Okay. Let's say, for example, in the forensic. Okay. In the forensic study, you found that a suicide case, and you suspect for arsenic intoxication. Therefore, please choose the appropriate spectroscopy techniques. So, which one you should choose? Atomic spectroscopy or molecular spectroscopy? For that example, if you suspect the victim, or the gender committed suicide by taking the arsenic compound AS, so you need go to the atomic spectroscopy instead of molecular spectroscopy. Or the question can ask you like this: analyze the analyze of the suicide case suspected for arsenic intoxication using molecular spectroscopy. As the forensic investigator, describe if the technique is correct or wrong. Please briefly discuss your reason. Okay, that is an example of question can be asked. Okay, so for the atomic spectroscopy, measurement of the wavelength or intensity of light that is emitted or absorbed by free atoms. So it need to be free. Okay, require high energy for excitation. Okay, to break the compound into the single element, we need a high energy. Okay, so when you want to analyze element, you need a very huge energy. That goes for the atomic spectroscopy. For the molecular spectroscopy, the energy is not that huge. To do this type of measurement, a sample must be converted into atoms. Okay, that's related to above sentence. You need to convert. You can only analyze for the atomic spectroscopy, you can analyze free atoms. Okay, to do that, you need to convert into atoms. How to do that? You need a very high energy for excitation. Okay, examples of atomic spectroscopy is atomic absorption spectroscopy, atomic emission spectroscopy, and so what. Okay, so the question can ask, if this question is very simple, you can just ask, please define atomic spectroscopy. Okay, So define, you can just define this. Yeah, let's say it's 2 marks. Let's say it's 3 marks. So you need to give an example. Okay, that's kind of the question can be asked during the examination. Okay. Okay, let's go to the molecular spectroscopy. Molecular spectroscopy of the interaction of light with molecule, or we can call interaction of different frequency of electromagnetic radiation with molecules. We can also mention, right now I just mentioned light, but if you want to write as the interaction of electromagnetic radiation with molecule, it's much more correct. Okay, molecules can absorb, emit and scatter light, require less energy for excitation. Okay, compared to the atomic, we don't need high energy, we don't need to break the bond. All of these interactions allow us to know the identity of and the structure of the substance. Okay, same goes to the atomic spectroscopy. We can somehow try to identify the atoms, but if you do the atomic spectroscopy, it's very hard to trace back the compound. If you want to know the compound or molecule, you need goes to the molecular spectroscopy. Okay, you cannot perform using atomic spectroscopy. Atomic spectroscopy only for free atom, free ions. Okay, example of the molecular spectroscopy is the UV vis and also infrared spectroscopy. Okay guys, again I would like to remind you guys, we have a group WhatsApp for this subject. So if anything you guys not be able to understand, you can ask anything over there and I'll try my best to answer your question. Alright. Okay, the next one we will look into the Lamberts Law. Okay, in the Lamberts Law we have 3 statements here. The first thing is the absorbance is linear to concentration. Okay, as we know, the higher the concentration of your analyte of interest, or the higher the concentration of the absorber, the more analyte will be absorbed by the absorber. So it means that the higher the concentration, the more height it will be absorbed by the absorber or analyte of interest. The next, absorbance change exponentially as function of linear change in the transmitters. Okay, what I mean by that is this. Okay, let's look here. Okay, at a full absorbance, there is zero transmittance. It means that everything getting absorbed by the analyte. Okay, again I repeat. Okay, if we look over here, at zero transmittance, it means full absorbers. It means everything absorbed by the analyte. Okay, so analyte was totally absorbed. Okay, again, let's say here the light get absorbed everything over here, so the total absorb, so there is no light transmit to the other side. Okay, again, okay, light go from here, be absorbed by the analyte totally without be able to transmit to other side. This is what is mean by here. Okay, so let's look when the transmitter is 100%. It means nothing absorbed by the analyte. It means that everything just pass through. Everything, all the electromagnetic radiation you apply is not getting absorbed by your analyte. It's just pass through the analyte or pass through the absorber without getting absorbed. That's why if we look over here at the 100% of transmittance, the absorbance is zero. There is nothing getting absorbed by the analyte. Okay, same goes to the transmittance over concentration. At the very low concentration, it means that less light to when the concentration is lower, it means that huge amount of light will be transmit. Okay, if your concentration is higher, the transmittance will be low. If you look over here, if your concentration is lower, the transmittant will be higher. Why? Because as the concentration is much, there's a lot of analyte, there's a lot of absorption happen. So the transmittant at the high concentration, the transmittant will be very less due to the absorption. More or less, it's about the same. Okay, so it is not impossible, okay, to understand this. Okay, so again I repeat, the concentration is linear to the absorbent. The higher the concentration, the more the radiation will be absorbed. Okay, for the absorbance, change exponentially in the function of the transmittant is mean by that the higher the transmittant is mean it show less absorption. For the concentration, at the high concentration, less light to be transmit. So let's say the question asks you, please describe graphically the three statements of Beer's law. So you guys need be able to understand this. Okay, that is kind of question that can appear in the examination. Okay, in Lamberts Law, we can calculate the concentration of analyte based on the absorption. So here is the formula. A, molar absorptivity. B, the path length, and C is the concentration of the substance. Okay, so here is the very easy formula, and I believe hopefully if the question be asked, I should not be able to give the formula. So I hope you guys can remember this lah. If I'm kind enough, for sure I will give the formula during the examination. But don't worry, if you are not able to remember the formula, you can always ask during the examination. I don't think there will be any problem to provide you guys with the formula, but it is very easy, so you guys should be able to remember. Okay, at least the A equal to this one, molar absorptivity multiplied by path length multiplied by the concentration of the substance. Okay, if you look here, we have another kind of formula. It's not that easy compared to here, so I think it should be distributed during the examination or test. Okay, to understand the transmittant, T equal to P of the after the pass through the absorber to the light of the incident. Okay, so P naught is the incident radiation, P is the transmitted radiation. This is the P. This is the transmittance. Absorbance equal to negative log T. Okay, and A, absorbance equal to also log 10 P naught over P. Okay, right? So okay guys, the next one we will learn about the Beer and Lamberts law. Beer-Lamberts law. Okay, there are three statements of Beer-Lamberts law. First, absorbance is linear to the concentration. What I mean by that, the higher the concentration, the more analyte, the more absorber it is that can absorb your analyte. So the higher the concentration, the higher the amount of the absorbers will be absorbed by the analyte. Okay, the next one, absorbance change exponentially as function of the linear change in the transmittance. Okay, if we can see here over here, at the very low transmitter, the absorption is very high. It means that, okay, let's say here is your sample cuvette, and the blue one here is your sample. Here is your incident. At zero transmitted, it means nothing being transmitted to the other side. Nothing being transmitted into your detector. It means that everything getting absorbed by your analyte. Okay, you get what I mean? Okay, if your there is nothing transmit to the detector over here. Let's say here is the incident. the incident radiation, and when it passes through the sample, everything getting absorbed. Okay, everything getting absorbed, it means that nothing getting transmitted. Vice versa, when everything getting transmitted, nothing being absorbed, it means that no absorption with the full of transmitted. Okay, this is what it means by the second one. Okay, the third one, transmittance is exponentially dependent on the concentration. Okay, the higher the concentration, the more analyte will be absorbed. It means nothing getting transmitted. So if we see over here, at the high concentration, less of the light getting transmitted. At the low concentration, when the analyte is not that much, a lot of light can be transmitted, so the percentage of transmittance will be high. Okay, here is the formula for the Lamberts law. Will be included in the calculation. It's not be impossible to be asked in your final examination test. But don't worry, if you guys are not able to remember the formula, or the formula is not given during the test or examination, nothing's harm. You guys can just raise your hand and ask the formula. Okay, we have four formula. A equal to EBC, I just call it as E, or molar absorptivity, the path length, and the concentration of this substance. Okay, the path length is the path length of the cuvette. It's mean the path length of the light need to pass through your absorber. For example, you have the cuvette over here, or the case of the container over here. The length of the light will be past the absorber. That is the path length. Concentration, of course, the concentration of your analyte over here. Molar absorptivity is the molar absorptivity of the compound. Okay, the molar of absorptivity for the certain compound should be constant. Okay, for example, compound A, it has its own molar absorptivity. Compound X, it has its own molar absorptivity. Molar absorptivity supposedly constant. Alright. The next formula is transmittance T P over P naught. P is the transmitted radiation, which is the one that pass through your cuvette or container over here. The P naught is the incident radiation. Okay, so P over P naught is the transmitted. For the absorbance, also is absorbance. Besides of this formula is also this formula equal to negative log T. Okay, or log P naught over P. Where is the minus missing? Minus missing is missing. Minus missing is missing because of this one. If you look, T supposedly to be P over P naught, right? If you remove the negative sign, it should be reverse, P naught over P, the incident over transmitted radiation. That's why the missing minus. So a lot of students just somehow forgot. Let's say they use negative log T, but sometimes they are make a mistake by using P naught over P. So you need to be very careful to use the formula. So if you don't remember the formula and the formula is not given during the examination or test, you can always ask for the formula. So it can be given to you, but I think it's very easy to be remembered. Okay, let's go to some exercises to the Lamberts Law. Okay, the molar extinction coefficient or molar absorption coefficient of the compound is 3 times 10³ liters cm per mole. Okay, if the absorbance reading at 350 nanometer is 0.9, Using a cell of 1 centimeter, what is the concentration of compound in the sample? Okay, so you have your formula. If you don't remember, you can ask, or it's not being given, you can ask the instructor. Okay, I always listed my my information. For example, the absorbance here. Sorry, why it's getting back. So I always listed the information based on the formula. For example, the given the formula, the question asks you about the concentration. So we want to know the concentration of the target compound. So what is the information we have? Okay, what is B? B is the path length. Okay, the path length using a cell of 1 centimeter. So we have the path length 1 centimeter. Okay, the next one you have is the molar absorptivity. So you have about what? 3000 liter per cm per mole, cm mole, if I'm not mistaken. Okay, so what is your absorbance? Okay, if the absorbance reading at 350 is 0.9, so the absorbance is 350 or 0.9? Okay, the absorbance is 0.9. The absorbance doesn't have specific unit. Okay, let's go to the, so you have the information already, so you just somehow rearrange the formula to find the concentration. So to find the concentration is equal to absorbance divided by E multiplied by B, molar absorptivity multiplied by path length. Okay, let's look at the answers. 0.9 divided by the 3000 multiplied by 1 cm, so you get 0.0003 molar. Okay, this is how you apply the Lamberts Law formula. Okay, but believe me, the question of the test or final examination, if the question appear, it will not be easier than this. This is very easy question. We will give the question that will be 10 times much harder. Okay, I believe so lah. So don't worry, you can always go through the past year examination, or you can find any other kind of question online. You can practice by yourself. I believe I will give some extra practice question in the e-learning. Okay, here is the next exercise. The level of the difficulty from 1 become 3. Okay, a sample in 1 centimeter cell is determined to transmit 80% of light at a certain wavelength. If the absorptivity of a substance of this wavelength is 2.0 liter mole per cm, what is the concentration of the substance? So again, the question needs to want to look the concentration of the substance. So again, you have this formula A equal to EBC. You need to find C. So what is C? You don't really know. So B, you have centimeter, 1 centimeter. You have the molar absorptivity, 2.0 L mole, -1 cm, -1. So, but how about A? You don't have the information about A. So you don't have two things. You don't have two things. first, you don't have the absorptivity, the absorbance, and you don't have the concentration. The concentration is what you look for. So if thing that we look for, we should look for the last thing. Okay, so you need to find the information of A. So you need to remember that we have another kind of formula to calculate the absorbance. A equal to negative log T, or A equal to negative log P of the emitted over P of the radiation, or equal to log P of the incident over P radiation. Okay, so let's look to the how the answers. So negative log 80 over 100, so the percentage, you get 0.097. Then we solve the equation. Okay, so to find C, A divided by molar absorptivity multiplied by the path length. So 1 cm multiplied by 2.0 blah 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 blah, you get 0.048 molar. Okay, molar, the other unit is is mole per liter. Okay, if you cut the unit cm multiplied by cm, 1 divided by everything, so it will be reverse mole over liter. So mole per liter is molar. Okay, don't get confused with the unit. So let's say for the example, the question is not asking about the finding the concentration. The question asks you find the molar absorptivity. Make sure that you are able to get a correct unit for the answers. Let's say if you don't get the correct unit, or you don't put the correct unit, the mark can be deducted. Okay, the mark can be reduced if you don't put the right unit. Okay, the next one we will learn about the types of spectroscopy. There's a lot of types of spectroscopy techniques, or we can call a lot of types of spectrometry instrumentation, which is fluorescence spectroscopy, X-ray spectroscopy, blah 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 blah, until mass spectroscopy. We have a lot of common types. We will not be able to learn everything, and we will look into the most common spectroscopy technique. For example, the UVVs, the IR, the mass spectroscopy. But I believe mass spectroscopy we will learn in the another chapter. We will focus on that chapter alone. Okay, we will learn about the flame spectroscopy, atomic emission, atomic absorption, atomic fluorescence, for example. But we will not learn everything. We will learn about the important one. Okay, let's look into the basic components of the spectroscopy instrument, or the basic component of the spectrometer. Okay, here is the basic component. We have the light source. Okay, the light source, and then after that we have the monochrometer, and then we have the sample compartment, and then we have the detector. Okay, we don't have the animation. Okay, we have the animation. Okay, the light source will go through the monochrometer. At the monochrometer, only selected radiation or selected wavelength of the selected type of radiation will pass through and reach the sample. At the sample, the transmitters will be the radiation will be absorbed. So at detector, we will calculate the amount of the incident radiation that is absorbed by analyte. Okay, again, here is the basic components. We have the light source, monochrometer, sample compartment, and detector. The function of light source to give, of course, the source. The monochrometer is to isolate the radiation into the selected wavelength that you selected frequency of radiation that you want to interact with your analyte. In the sample compartment here and here is the place that we put our sample. And then at the detector, the function is to calculate or detect or reach or somehow manipulate the data of the radiation that's actually being absorbed by the absorber or analyte of interest. Okay, here is another illustration of the spectrometer, but it's a little bit complicated, I can say. Okay, here we have the light source, and then here diffraction grating act as the monochrometer. Okay, here we have the isolation slit to only allow a single wavelength or single frequency to pass through to interact with our analyte. Okay, here is our detector. Okay, for example, here we have the source, we have the entrance slits, and we have the exit slit. The function of entrance slit over here, both of here, is to remove the interference of lights from the other source. Okay, we want only to focus the single source of light before it can reach the monochrometer. That is the function of entrance slits and exit slit. Okay, here we use the diffraction grating. Here we can see in the form of a prism. Okay, basically we have a lot of kind of monochrometer. There is a kind that use diffraction grating. There is a kind that use a prism, and also there's also other kind of monochrometer system. Okay, but here we talk about the diffraction grating and also prism. Okay, so what happen? The light source will give the light and reach your monochrometer, and the monochrometer will only allow will somehow disperse your light into multiple frequency or multiple wavelength. Okay, at the exit slit, only one kind of frequency or one kind of wavelength will be passed through and reach your sample, and then after that it will reach your detector. Okay, again, if anything, you guys can always WhatsApp me, or I prefer you WhatsApp in the group so we can share the information within the group. Okay, here is the example. We have the light source. Okay, in the light source we have only single light source, so it's still not splitted into the respective frequency. At the diffraction grating, after that only it will somehow separated into different frequency. But at the exit slit, we set which one of the frequency that we want to pass through to reach the sample. Okay, and then it will reach the detector. If we can see here, here is the light source, here is the diffraction grating. Okay, so from the diffraction grating we select the incident light. Okay, for example, here right now is purple, blue, and then it goes to yellow, it will go to orange and red. If you can see again here over here, you can see the pattern. The amount of light over here is much more higher compared to here, because some of it absorbed or by the analyte of interest. So from here, the P incident over P of the transmitter, the incident, can shows the absorbance, or we can calculate the absorption. Okay. Alright, the next one we will look about the components of lights or excitation source. if we learn back in the first few slides, we have range of kind of radiation from the gamma radiation until radio wave. Okay, so the light source will somehow provide a range. For example, from for UV is from 200 to 400 nanometer. At the monochrometer, there is where we only specific the range into a single frequency. For example, we want to specific to 251. So at the monochrometer, we did that. Okay, but at the light source, it will somehow provide the range of the radiation. For example, X-rays range, UV range, vis range, IR range, and also the other kind of range. This provides sufficient amount of light which is suitable for making measurement. For example, you want to analyze UV, so it will provide the light source UV should be sufficient. The light source typically yields a high output of polychromatic light over a wide range of the spectrum. Okay, the light source typically yields a high output of polychromatic light over a wide range of the spectrum. Okay, normally, for example, like I said before, if you want to analyze the interaction with the UV, so you need to find the light source that cover the range of UV. Okay. Polychromatic is the vice versa of the monochromatic. Monochromatic is single, polychromatic is multiple. So in case of the UV, it's supposed to cover from 200 to 400. If you talk about the UV rays, so it will cover from 200 to 700. If you talk about IR, you need to cover from 2500 to 500 micrometer, from the 2500 of nanometer to 500 of micrometer. Also with the other kind of the interaction. Types of light source used in the spectrophotometer includes incandescent lamp and also lasers. Okay, lasers we use when we want to find the interaction with the higher amount of energy. That is when the lasers will be employed. Okay, the next one we learn about the component, specific component of light source again. You guys don't need to remember very specific. You guys just need to understand the basic understanding, the basic knowledge of it. Don't need to remember everything over here. Okay, alright. So we have here in the kind of incandescent lamp, including the tungsten lamp and deuterium lamp. If we can see over here, to analyze UV from 200 until 700, we need both from deuterium and also tungsten. So from the UV range 200 until 400 can be covered by deuterium, and the others range can be covered by using tungsten lamp. Okay. Hydrogen gas lamp and mercury lamp can cover from 200 until 800. Okay. And also for the infrared radiation, we need glow bar 100 to 400 nanometer, and also the other thing. But you guys don't need to remember. But the question can ask you guys about the light source. For example, give this chromatogram, give this graph, and then you need you guys to deduct. For example, okay, from the analysis, okay, the higher absorptivity of the analyte falls under 800. Okay, decide which kind of lamp are suitable for the analysis of the analyte. So you need to able to write that tungsten lamp is the most suitable lamp or light sources for that kind of analyte. Okay. If there is any question, you can always write in your WhatsApp group. Okay, the next one we will learn about another kind of light sources, which is the laser source. This device transforms light of various frequency into an extremely intense focus and nearly non-divergent beam of monochromatic light. For the laser, is very intense. It's focused on the single wavelength. When we want to interact our absorbent at a very high intensity of light, that is when we use laser source. Okay. The unique property of lasers include spatial coherence, a property that allows a beam diameters in the range of several microns, which means very specific. Production of monochromatic light with no interference of other kind of wavelength. So it's very specific. Have pulse width that vary from microseconds to nanosecond or to picosecond. Okay, it means that the analysis will be very sensitive or very focused. However, the source is expensive lah. Okay. The example, the analysis that using laser, including the, if I'm not mistaken, Raman spectroscopy. Because why? For Raman spectroscopy, we need to use laser because Raman, because we learn already the scattering, the amount of scattering is only about what, 0.0001%. Okay, the amount of the interaction of with the analyte very minimum. That's why we need to use a huge intensity of source so we can read the scattering better. Okay, that is why Raman spectroscopy use laser. Okay, for the time being, I don't remember if there is a Rayleigh spectroscopy, but I believe for Raman spectroscopy, yes, we have at the faculty, and actually one of my students' project use Raman spectroscopy. Okay, next we will learn about the second components of the basic components of spectrometer. Okay, the next one is the monochrometer, or we can call that as the spectral isolation system. Okay, monochrometer is a system for isolating radiant energy of a desired wavelength and excluding that of other wavelength is called a monochrometer. Okay, it means that we have the entrance slit, we have the light source. Polychromatic. Polychromatic is mean have a lot of range of wavelength. Okay, this system we call as the monochrometer. So when it's enter the entrance slit as the polychrometer, and then it will go transformation from the polychromatic into monochromatic. At the diffraction grating here, for example, one of the system for monochrometer is separating the polychrometer into monochrometer of wavelength or monochrometer of radiation. And then from the diffraction grating, we can adjust which kind of wavelength or which kind of frequency that we want to allow to enter the to exit the exit slit to reach our sample. Okay, monochrometer consists of these parts: lenses or mirrors to focus the radiation, entrance and exit slits here and here. The purpose of entrance and exit slits to restrict unwanted and control spectral purity of the radiation. Okay, and then the third component of the monochrometer is dispersing medium. Okay, this is the dispersing medium. Okay, in dispersing medium, we have three kind of common dispersing medium, which is prism, diffraction grating, and filter. So it can be asked in the test or examination, okay, please describe the parts of monochrometer. Okay, so you need to mention these three: lenses, mirrors, entrance and exit slits, and dispersing medium. Okay, please state three different kind of dispersing medium. So you need to able to understand the difference between prism, diffraction grating, and filter. Okay, so these are three parts. The first thing first, we have the mirror. we have the entrance and exit slit, and the third one is the diffraction grating. Is it okay if you want to say the first one is diffraction grating, the second one is mirror, the third one is exit slit and entrance slit? Is also okay. It doesn't matter as long you are able to state these three parts of the monochrometer. Okay, the next one we will learn about specific kind of dispersal medium. The first one is diffraction grating. Okay, I hope you guys don't memorize all of these words. Okay, don't memorize. You need to understand. Okay, so here is the components: entrance slit, exit slit, diffraction grating, mirror. Okay, so if you just able to describe this thing, I think you can answer greatly. Okay, don't need to memorize all the words inside this slide. Okay, so here we have the light source. The rays or the beam will focus by hitting the mirror and then will be reflected to diffraction grating. Okay, so the ray polychromatic light will focus to diffraction grating through focusing adjustment from collimating mirror. Okay, then after it hits the diffraction grating over here, it will diffract into different wavelength. It will somehow separated into different wavelength. So you can use any kind of words that can easily you guys be able to understand. Doesn't matter. Don't memorize as words by word in this slide. And then the orientation of diffraction grating is direct only one narrow band wavelength to the exit slit of the monochrometer. So here we have the focusing mirror. Okay, we have the focusing mirror. We have here focusing mirror. At the diffraction grating, it will separated into separated wavelength. So at the focusing mirror, it will somehow narrow the separating wavelength to the exit slit. Okay, rotation of the grating. We actually can rotate the diffraction grating to somehow allow a specific kind of wavelength to reach the exit slit. Okay. After that, then the selected wavelength or selected frequency of radiation can reach the sample before it reach the detector. If we look again over here, where is it? Where is it? Okay, if you look again over here, the diffraction grating can be adjustable. So we can allow to focus a selected wavelength to somehow reach the exit slit before it can reach our sample and also detector. Okay, so it's very easy. You just need to know the basic, then I think you can describe the thing. Here is the same figure. Okay, the next one we will learn about the next monochrometer system is a prism. Okay, dispersion by prism depends on refraction of light with a wavelength dependent. Violet color with a high energy are diffracted or bend the most, while the red light with the lower energy are diffracted or bend the least. Okay, so I don't need you guys to remember everything. You can just say that the prism is there where it diffract the lights or bend the lights. The one with the high energy will bend to the other side. The one with the lower energy will bend to the other side. As a result, the polychromatic light will somehow disperse into individual lights. Okay, so I don't need you guys, please don't remember a lot of things. So here, instead of in the diffraction grating, we use the diffraction grating to rotate, right? But in the prism, usually we adjusting the exit slit over here to actually focus in which rays we want to select. Okay. Right. Okay. Here is the example of prism. Okay. As I said before, we have the light over here. At the prism here, it will somehow disperse into range of different kind of wavelength, and then at the exit slit, we change or we move the location of exit slit to only select the selected wavelength or the desired wavelength. Okay, here rotation, prism rotation, we can also rotate the prism and we can also move the slits. In the figures, we can move the slit. Okay, in here we can do rotate. I think the both concepts are acceptable. Okay, the next one we will look into the filter, one of the other dispersive medium of the monochrome-meter. Okay, in the filter we can divide it into absorption filter and interference filter, but you guys don't need to remember specifically any of these. But the concept of the filter is absorb or reflect the unwanted wavelength and then only allow the desired wavelength to pass through the filter. I again repeat, the filter, the principle behind it is by absorbing or reflecting the undesired wavelength, and only allow a desired wavelength. Okay, we have two kind of filter: absorption filter and interference filter. Okay, here is the pictures. Okay, right, if we can see here in the interference filter, it has a glass, metallic film, dielectric material, and so a lot of other things. Okay, in the principle here, it's reflecting other things instead of our target specific wavelength. So it will reflect, it will not allow other kind of wavelength to pass through except for specific wavelength. In the absorption filter, it's absorb all the kind of wavelength except of the desired wavelength. For example, here we have the green filter. So we have the purple filter, so it will somehow allow blue and red to pass through. Other than that, it will not be allowed. But the disadvantage, they are not very good reference selector and can be used in instrument utilized in research because they allow the passage of broad bandwidth, which give a chance for deviation from Lamberts law. So it means that with the filter, we are not somehow separating into a single wavelength. We actually kind of beam all the polychromatic into a single lens, and then we allow only a single wavelength. Okay, which is, it can somehow put the deviation from the Lamberts law. And also they absorb a significant fraction of the desired radiation. It means that the radiation, okay, the desired radiation instead is not really effective. Okay, it's not really effective. It reduces the power of radiation significantly, so it cannot it is not effectively somehow will be absorbed or react with our absorber or analyte of interest. Okay, so this kind of question can be asked. Okay, please describe the disadvantage of the filter as the monochromator compared to the others. Okay, so we know already the disadvantage of filter as the monochromator. We also learn about the other things. Okay, the next one we will learn about the components of the sample compartment cells. Cells are selected appropriately based on the wavelength of requirement. Okay, for visible and UV spectroscopy, a liquid sample is usually contained in the cell called a cuvette. Glass is suitable for visible but not for UV because it absorbs UV radiation. Quartz can be used in UV as well in visible spectroscopy. Okay, this one I need you guys to remember a little bit because we only have 3 kinds. so it's very easy for us to understand. Okay, we have three kind of sample compartment. It's the quartz, silica glass, and plastic. Okay, to analyze UV until visible range, you need to use quartz. Okay, you need to use quartz, which is a fused silica. Okay, and then the next one we have silica glass, the normal glass lah, the normal glass, which is can somehow cater from 350 a part of the UV until the visible, but not a very good range of UV. Okay, plastic only allowed from 300 and above as well. It's not very good as well. Okay, so let's say the question asks you have the certain compound, the wavelength is 235. Please advise the sample compartments that's suitable for the analysis. Discuss why. So you guys need to be able to understand the concept. Guys need to be able to describe. Okay, for example, okay, you say okay, the best silica, the best sample compartment is quartz because it can allow the analysis from 220 nanometer wavelength. Okay, if we use the silica grade plus, which is the range is more than 300 nanometer wavelength, the incident range at 235 will be greatly reduced by the compartment before it can reach the sample. So it will reduce the efficiency or accuracy of the analysis. Okay, so by that explanation, you can reach about 2, 3 or 4 marks depending how you understand the concept of this kind of the sample compartment. The best one is quartz. Okay, so let's say for example the analysis wanted you to analysis from 320. Okay, so how you can select the compartment cells? You can suggest quartz and plastic but not silica glass. Why? You need to describe. Okay, but if you are prefer, you need to discuss a little bit more. Plastic is advisable because compared to quartz, the plastic is more cheaper and durable. Okay, that's the other thing lah. And in this kind of analysis at 320 nanometer does not need quartz to be used. Okay, so that is how you can answer the question. So I actually love a lot to give an idea how the question can be asked to you during classes. Okay, but sometimes the question can be hard. Okay, for example, okay, the forensic team has received a sample of drug, blah 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 and blah 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 blah. Okay, upon the initial investigation, they found the compartment, the wavelength of the maximum wavelength of the absorption of the particular compound is at blah 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 blah. Okay, please describe how you select the compartment cell of the analysis. Okay, that is how we can somehow change the tone of the question, the color of the question to make you guys think deeper and deeper. Actually, the question is very easy. Okay, the analysis is at 350. Okay, please select a suitable compartment. But of course, in the examination, the question can be changed into the hard mode. Okay, so just be aware. Okay, the next or the last components of the spectrometer is the detectors. The detectors are devices that convert radiant energy into electrical signal. So from the light source, it will convert into electrical signal. Okay, why? Because we want to read the data. A detector should be sensitive and has fast response over considerable range of wavelength. In addition, the electrical signal produced by detector must be directly proportional to transmitted intensity. Okay. Okay, let's say the question asks you guys like this. Please describe the prerequisites for detectors. Okay, Mean that prerequisite is mean that the terms and condition for that detectors before it can be used in spectrophotometry. Okay, the detectors device that the first thing first, it can convert radiant energy into electrical signal. If not, it cannot be detector. And of course, detector should be sensitive and have fast response. We don't want our detector is less sensitive. And the third one, okay, it must be directly proportional to the transmitted intensity. It means that as if the transmitted is higher, so also with the, it must be linear with the intensity. Okay, if the transmission is higher, we need the higher electrical signal, so it must be directly proportional. Okay, we have a lot kind of detector. The first, we have the barrier layer cells. Next, we have phototubes. The next one, we have photomultiplier tube. And the next one is the photodiode array. Okay, I don't need you guys to remember a lot of things. Okay, maybe you guys need to remember one or two. That is much easier for you. Okay, next we will learn a little bit about the detectors, specific detectors, but please don't memorize everything. You need to just understand the concept. Okay, the first detectors that use in the spectroscopy is the photovoltaic cell, or we can call it as the barrier cell. If you look in the figure over here, above we have the glass, and above, if we can see, we have a few layers over here. The first is the glass. We have the thin layer of silver or gold, and then we have the selenium, we have the iron. Okay, and the glass is just the one that protect everything inside here in the system. Okay, and the thin layer of silver here can be changed by using gold also. It acts as the electrode. Okay, it's very thin, so that the your light, or your what we call as the light radiation, can go pass through and directly reach the selenium. Okay, the next one, we have the iron. Okay, so again, the above one, we have the thin layer of silver and gold. Okay, act as electrode. And we have the selenium. Okay, we have the selenium layer, and we have the iron as the another electrode. Okay, the selenium act as the semiconductor. So when it's happened, when the radiation come from above, when the radiation come from above, okay, reach to the selenium ion, selenium semiconductor, the electron that on the selenium will become mobile. It will move. When the electron excited or electron moving, it will somehow produce a current. The current is the what that read by the data reader. Okay, it's what read by the computer. Okay, the flow of current observe proportional to the intensity FF length of light falling on it. So the more the light ray come into contact with selenium, the more mobile the electron. Okay, that's how the detectors works. The concept is about the same with kind of every detectors, but the photovoltaic side is no longer commonly used because the sensitivity is not that great. We have other kind of detector which is much better. Okay, so please don't memorize everything, just understand the concept that we have the layer that the light rays need to fall upon us, and we have the electron in between. So when it's enter the layer, it can create a current, and then the current will somehow read by the data reader. The intensity of the current mobile or the current flow is depends on the type of wavelength and the intensity of the light fall into the semiconductor. Okay, that is the concept for the photovoltaic side. Please don't remember everything. Alright. Okay, sorry, please don't memorize everything, but you need to understand the concept. Okay, the next detectors is phototubes or the photo emissive tube. The phototubes is the most common detector because it has more sensitivity compared to the barrier layer cell or photovoltaic cells. Okay, if you look over here, the phototubes we have the outside here is the glass. Okay, and we have the two electrode, cathode and anode. The electrode have the coating of calcium, silver oxide or mixture of them. Okay, which is made the photocathode become sensitive. Okay, become photosensitive. So when the radiation came after it's reaching, sorry, let's say here is your sample, here is your light beam. Okay, then it will reach your detector. Yeah, and then it will pass through and hit the cathode. Okay, or you can just say hit one of the electrode. When it hits the electrode, the electron from the electrode, the cathode become mobile and attracted to anode. Okay, remember electron is negative, right? So it will always go to anode because anode is positive. So when the electron goes to the anode, again it will produce a current flow. It will produce a current flow. Same goes, the same concept. The higher the intensity, different wavelength will affect the production of the electron. Okay, the more the light ray pass through, okay, the more electron will be produced and reach the anode, and also will create a potential difference before we can read by our data reader, by the computer lah. Okay, so okay, don't memorize everything. You just need to remember the concept or understand the concept. Okay, we have the barrier cells, we have the phototubes, and next we will learn about another detector. Okay, the third detectors that you guys will learn is the photo multiplier tube. Okay, if you compare to the phototubes and the photovoltaic cell, it's just one process. So it hit, it create a potential difference, and then it will produce the current flow. Same goes to here. But in the photo multiplier tube is a little bit different. Okay, so I just go directly. Okay, here is the photo multiplier tube. When the light reach the photocathode, it will somehow produce the electron. Okay, electron produced will hit another photocathode. Okay, the process is repeated with the number of electron multiply each time it hits the another photocathode. Okay, so we call this as the diodes lah, diodes. Okay, so then the electron, where at the final destination it will reach the anode, instead of only one electron produced, when it reach the anode it will become much more greater. Okay, so the sensitivity of the photomultiplier tube is much more higher compared to other detectors. Okay, that is the concept of the photomultiplier tube. Okay, so if you're asking me what is the best detectors out there, I would like to say is the photomultiplier tube, but of course the price is expensive. Okay, let's say in the situation where you somehow confronted the sample is very trace, it's very minute. Okay, it's very minute, and you believe that the concentration of your analyte is not that great. The concentration or the analyte is diluted, or the analyte you believe is not that much. For example, for explosive, okay, when it's exploded, a lot of explosive will gone by, so it will somehow burn. So the remaining explosive will become very trace. So you need a very sensitive detector. So that is how you can suggest what kind of detector. For example, photomultiplier tube. And then you can also describe why you choose the photomultiplier tube. Okay, because it's very sensitive to light. And maybe the question can ask, what is the mechanism and what so and what. So you don't need to remember everything. You just need to understand the concept. Okay. Okay, the next detectors is the photomultiplier tube. Okay, here is the schematic figure of the photomultiplier tube. Okay, again, here we have the light source. Okay, or after, here is, for example, here's your sample, here is your incident light, and here is your emitted light. Okay, when then the first your emitted light will reach the photocathode. Okay, if we compare to the previous detector, the process is only occurs once. It doesn't repeat. So for example, here when it reach uh the electrode, it will produce the ion, and then you get the current flow, and then you get the data reading. Okay, same goes to the phototubes. You get everything only once. But the photomultiplier tubes is involve the process of multiplying of the electron. That's why we call as the photomultiplier tube detector. So again, the light will somehow reach the sample, and then the emitted radiation will go to the photocathode. Here, it will produce the electron. Okay. So what happened after that? We have several diodes. Okay, we have several diodes. Okay, maybe 8 to 10 diodes. The diodes is also kind of photocathode. Okay, so for example, we have the single electron here, reach the another diodes, so it will multiply 2 multiplied by 4, 4 multiplied to 8, 8 multiplied to, for example, until 40, something like that. Okay, for example lah. Okay, right. So instead of only one electron, it will reach the anode, the ample of that. Okay, all right. Let's say you have 1000 electron, it become 2000, it become 4000, 4000 become 8000, 8000 become 16,000. So it increase the sensitivity considerably. Not considerably, we can say very hugely, very greatly. It's increased the sensitivity of the data reading. Okay, sensitivity of the detector. So that is the advantage of the photomultiplier tube. It's very extremely sensitive. Okay, however, of course, the photomultiplier tube is expensive. Okay, is expensive. Alright. Okay, let's say you have in a situation when you have received a sample that you believe is in trace in number. For example, you encountered the bombing cases, and then you need to find the explosive compound. Of course, after the explosion, the amount of the explosive left, the amount of compound left of the explosive will be very little. So you need a kind of very sensitive detector, which is, I believe I could suggest the photomultiplier tube. Okay, so that is kind of situation or the kind of problem that you need to solve. Okay, right. Here is the other figures. Okay, but I don't want to really focus. Please don't memorize everything. You just need to understand the concept. So now we already learned three kind of the detector. We have the photovoltaic barrier cell, we have the photo tube, and then now we have the photo multiplier tube. Okay, please don't ever suggest photovoltaic cell as the detector. Okay, at least the photo tubes only. Alright. Don't ever suggest this lah. Okay. Alright. Okay, the last detector is the photodiode array. Okay, if you compare photodiode array to other detector, I love photodiode array. Why? Why is that? Because you can somehow analyze all wavelength simultaneously. Okay, not all lah. You can we can analyze multiple wavelength simultaneously. Okay. For example, here is the light source. We have the focusing mirror reach the sample. So it will reach the grating polychrometer. Okay, and then the grating polychrometer, instead of we have the exit slit over here to allow only a single wavelength, it's just somehow all the wavelength will reach the detector. Okay, for example here lah, the ray, we have their own photo cathode over here. 1, 2, 3, 4, 5, 7, for example. We have the diode array detector at the T05 Faculty of Science HPLC diode array detector. And if I'm not mistaken, it can be analyzed up to 12 wavelengths at the same time. So what is the best thing about photodiode array? It will reduce the time of analysis. Okay, but of course the sensitivity of the photodiode array is less compared to the photo multiplier. At one times the photodiode array detector is much less than photo tubes detector, which is our detector number 2. But nowadays they already improved the photodiode array, so it can somehow better than photo tubes detector. Okay, so the concept is the photodiode array, it can somehow analyze multiple wavelength simultaneously. Okay, but again the disadvantage is less sensitive than photo multiplier. Okay, let's say if the question or the situation asks you where you can apply the photodiode array detector. Okay, for example, you encounter a new kind of compound or drug compound, or we can say a design drug. Okay, the new kind of drug compound. So you want to perform the analysis, but you don't really know the best frequency of wavelength can be used to analyze that particular drug. So by using the photodiode array detector, you can analyze simultaneously multiple kind of wavelength. You can reduce the time. Okay, so the photodiode array detector is the best one to study what kind of the best frequency of radiation interacted with the target analyte. Alright. Okay, the next we will learn about the spectrometer design. Spectrometer design can be divided into two, single vs double beam. Okay, nowadays we still have this single beam, but only for teaching purposes. But most of the analytical lab, they will have the spectrophotometer. Why? We will learn about the advantages and disadvantages of single and double beam. Okay. Okay, of course, here if we can see in the single beam, it just goes directly, the light source will somehow pass through the monochrometer system, and then it reach the compartment cell or sample cell before it reach the detector. In the double speed spectrophotometer, we have this kind of schematic diagram. Okay, with for example, here is the light source, we have the mirror. So the ray goes over here, and the ray from this side will also reach the monochrometer. So we have the sample, we have the reference, and we will reach the detectors, and we can get the result simultaneously. Okay, where is the situation when we need the double beam spectrophotometer? Okay, I believe double beam spectrophotometer nowadays is required for every single analysis. It's better for every single analysis. Okay, why is that? Okay, single beam spectrophotometer is inconvenient because the sample and blank must be placed alternately in the light path. Okay, for example here, okay, first you need to run blank and then you need to run the sample. So it will take some times lah. For the measurement at multiple wavelength, the blank must be run at each wavelength. So remember, if you want to analyze at different wavelength, so for example, if currently you want to analyze at 300 and then after this you want to analyze at 400, so every time you want to change your wavelength, you need to run the blank and then you run the sample. So every time, for example, you want to run at 250 wavelength, so the first you run the blank at 250 and then you place your sample at 250. So it will take a lot of time, it will take a lot of energy. But if you use the double beam spectrophotometer, you have the sample over here, you have your blank over here, so you can just change the wavelength without the requirement you need to somehow replacing the sample with your reference or blank. So it's very efficient. Any fluctuation in the intensity of radiation sources affect the absorbent. Continuous spectrum is not obtained. Okay. Remember, single beam spectrophotometer, you need to change the blank and also the sample. So any fluctuation of the radiation will affect the absorbent. For example, you put the blank but it has different intensity during that time. Okay, but after that you run your sample, it has different kind of intensity. Maybe the intensity is not that much different, maybe about 5 to 10%, but it's still affecting the result. But if you use a double beam, we can somehow solve that kind of fluctuation because you run both at the same time. You don't have the kind of fluctuation in the radiation. Okay. Continuous spectrum is not obtained because why? In the single beam, you need to somehow change with the blank before you can run the sample. So you cannot just, okay, 200, next you want to analyze at 250. You cannot do that. Okay, you cannot do that for the single beam. Okay. But with the double beam, you can just change the desired wavelength. For example, right now you want to run at 200 and then you want to run at 220 and then you want to run at 270. Okay, you can run continuously without any what we call as the interval between that. Okay. In double beam instrument, it gives ratios of intensity sample and reference beam simultaneously. Fluctuation due radiation source are minimized because the two beams are compared and measured at the same time. Allows continued reading of spectrum, absorbent versus wavelength. So in this way, situation where is such one your suggestion why you want to use double beam instrument compared to the single beam instrument, you guys need to be able to describe this thing. Okay, so this is kind of the very famous question also in the examination. Please describe the advantages or please differentiate between the single and double beam design of spectrometer. That's kind of the question. Pretty famous, pretty common to be asked in the examination. Okay, I think that's it for the spectrophotometer. The spectroscopy part 1 for this class. I hope that you guys don't memorize everything, but you guys need to understand. Okay, by how you can understand it better, you need to find keep in your head the situation. For example, why you need this kind of components, why you need this kind of design, why you need this kind of thing. Okay, for example here, okay, where is the situation you need deuterium lamp. Okay, for example, the situation when you want to analyze the analytes between 200 and 400. Okay, that is the situation. You just need to imagine the situation so you can understand the analysis. You can understand the lectures. Okay. Okay, that's it, I think. Thank you so much. We will meet again at the next lecture.